There is,
Message has come that meeting
yeah,
is now streaming, right?
it's live streaming now.
Yes, it is live.
Yeah.
So
So,
start.
yeah,
Hmm,
Swapna, please go ahead.
right. So first of all, happy Guru Purnima, and then good evening, everyone. On behalf of Indian Association of Physics Teachers, I'm delighted to extend a very warm welcome to all the participants who have joined us for our online program, the lecture series on physics education research. So this initiative aims to nurture a vibrant community of physics educators, facilitating the exchange of knowledge and promoting continuous professional development. So our engaging physics education research series continues to thrive. And today we are excited to present the 14th lecture featuring another distinguished scientist. It's my honor to welcome Professor P.K. Ahluwalia, President of IAPT, whose visionary leadership has been pivotal role to the success of this series. I also extend a heartfelt welcome to Ms. Rekha Gorpade, Secretary of IAPT, whose dedication and support have been invaluable. It's my privilege to welcome today's speaker, Dr. Ajith Kumar, a distinguished scientist from Inter-University Accelerator Center, IUAC Delhi. Dr. Ajith Kumar will be sharing his profound insights on a tool for learning science through exploration and experimentation. The title of his presentation is Role of Experiments in Teaching Physics and Indigenous Effort. So welcome, Dr. Ajith. We eagerly anticipate your enlightening session. I extend a sincere welcome to Professor H.K. Sejwani, who will be chairing today's session. Professor Sejwani is a distinguished academician with a career spanning of over 34 years at the postgraduate college, where he served as principal also. His contribution to academia are marked by pivotal roles at ISC College of Engineering Technology, including head of the Applied Science Department and Dean Academics for a decade. His dedication to education and research is evident through ongoing R&D initiatives, particularly in innovative physics experiments utilizing Arduino technology. Professor Sejwani is widely recognized for his authorship of physics textbooks and its role in advancing curriculum development, particularly in nanotechnology for new BTech courses. So beyond academia, Professor Sejwani's professional engagements include presentation at national conventions, curriculum development for IAC University, and invited lectures on nanotechnology and science. His significant contributions have been acknowledged with prestigious awards, including the Man of the Year Award for the American Biographical Institute. So we welcome you, sir. I also extend a heartfelt welcome to all our participants joining us today. So before I hand over the mic to chairperson of today's session for further proceedings, I would like to invite Ma'am Rekha Godpade for sharing his opening remarks. So Ma'am Rekha.
Thank you, Swapna, and good evening and very warm welcome to all of you. I'm really happy that this kind of a series which we have started last year, IAPT PER lecture series under the leadership of coordinatorship of Sapna is continuing, and we are having a 14th lecture today. I think as committed by IAPT, we have been doing it for the uplift and upgrading the physics teaching among the teachers across the country. And we are equally having important component, which is a experimental component when we are teaching physics. And we have a very appropriate person today who is going to talk about the experimental contribution in as a role of in PR. So I welcome Dr. Ajith Kumar once again on behalf of IAPT and on my personal behalf. I also welcome each one of you who has joined. I also thank and welcome Dr. Sehjawani, who is a very, very active member of IAPT and takes very keen interest in IAPT activities. I remember even Dr. Sehjawani has conducted a workshop on this particular topic earlier. And now we have Dr. Ajith Kumar talking to us, which is going to be a very enriching experience for all of us as the teachers. So thank you very much, Sapna, and thank you, Dr. Ajith Kumar, for accepting our invitation to be here. And I wish a great success, and I'm sure that the participants are going to have a very nice time ahead. Thank you.
So thank you, Rekha ma'am. And now I hand over the stage to Professor H.K. Sejwani ji.
Thank you, Mr. Sharma. It's a great honor to introduce Dr. Ajith, a distinguished scientist and pioneer in accelerator physics and nuclear instrumentation. Dr. Ajith began his scientific journey with a BSc in physics from the University of Calicut in 1981, followed by an MSc in 1984. With top honors, he then pursued an MSc in accelerator physics from the University of Manitoba in 1986 and completed his PhD in nuclear physics from the University of the Calicut in 2008. Dr. Ajith professional career started in 1985 at the Inter-University Accelerator Center. He made significant contribution, pioneering progressing to Scientist H before retiring in February 2021. He has received prestigious awards, including S.N. Sheshadri Memorial Award for Instrumentation, the Award of Excellence from the Nuclear Science Center, and the Kenneth Gonsalves Award from the Python Software Society of India. I think it is because of the book that he has written on Python. Dr. Ajith's expertise spans through particle accelerator, nuclear physics, electronics, computer hardware, and software. He has been instrumental in designing and developing linear accelerator, beam dynamics, and RF resonator cavities for Linux. His work also includes developing a high-speed data acquisition system and instrumentation for fusion and fission studies. A remarkable aspect of Dr. Ajith's career is his role in establishing critical infrastructure at IUAC, including the RF and electronics laboratory and the high current injector facility. His innovations have led to the India's first PC-based particle accelerator, control system, and high-speed data acquisition system, advancing nuclear research capabilities. Moreover, Dr. Ajith has shown a deep commitment to education and training, leading the teaching laboratory at IUAC. His phonics project and EXPIs system have significantly impacted science education, making it accessible to many students and educators. Dr. Ajith Kumar career is a testament to his dedication, innovation, and excellence in science and education. His contributions have advanced nuclear physics and accelerator technology and inspired the next generation of scientists and educators. Please join me in welcoming Dr. Ajith Kumar, BP, as he shares his insight and experience with us today. Thank you.
So, over to Dr. Ajith. Thank you, Dr. Sejwani.
Thank you.
Sir,
Please
unmute yourself. Dr. Ajith, please unmute yourself.
Yeah, okay. Just muted that. Okay, good afternoon to all of you. And first of all, let me thank the IAPT organizers for giving me an opportunity to be here and meet all of you. And what I'm planning today is just the topic which we have mentioned is quite elaborate, physics education research, but I'll be talking about a very narrow region of that, like experiments and how we put some effort to make things a little bit easier for doing experiments. So I'll mainly focus on that. So let me just share some screens. Maybe I'll just put the desktop. Bit confusing. Okay, can you see this slide now?
Yes.
Yes, sir.
Okay. So let's start. And first of all, whatever I'm talking about, everything is documented on this website. I mean, these two websites, xpice.in contains all the information about xpice, and the scischool.in, some other material, which is my personal website. So first of all, let us mention the present situation. Like all of you know, our science education is heavily loaded with theory, and a small fraction of it is experiments. And even though experiments are mentioned, you can say now in the 4-year UG program, it is 30% of each paper. But practically, I mean, the effort put on the practical side is much less than that, because students get an impression that even if you ignore practicals, you know, it's okay kind of situation. And when we look at the progress in other areas and compare it with our scientific instrumentation. So you can see here the communication, we have moved from this kind of device, an old telephone set, to our smartphones. And transportation, the steam engine, to this new metro railway. But if you look at the lab, even 50 years back, you see the ballistic galvanometer, and the same thing you will find today also. So we have not progressed much. I'm talking about our Indian context, like designing new scientific instruments. It has not, you know, taken that seriously. And the alternatives, like if you see outside situation, there has been modern instruments which is giving you the computerized data acquisition and all facilities. And here I'm mentioning, say, 3 companies, say 3 major players like Pasco, Vernier, and Five. Five is a German company. And all sorts of modern teaching, you know, equipment is available from here. And some of them were actually imported also, like our ICERs purchased some of them, and Kanpur IAT had a lab earlier. But the problem with this, these are all proprietary solutions. That means, you know, you cannot copy them, or you cannot, you know, find out how it works, and they are not affordable. It is something like, you know, a couple of $1,000s, you know, for each experimental setup. That range it goes. So when we started this project around in 2005, so this was the situation. So what we found is actually experiments are often, you know, ignored in our science education. And one reason could be the lack of cost-effective equipment. And that could be only one reason. probably another main reason is like the competitive exams. Like if you want to, after +2, if you go for all kinds of, competitive exams for entrance exams, there the practical skill or experimental skill is not tested. And actually, one exception was the ICER's that project mode entry. That also, I don't know now it is available or not. I mean, without any entrance exam getting into ICER's. That path is, I don't know whether it is available anymore. And so what IUAC, what we thought is we had a lot of experience in developing instrumentation for the particle accelerator. So our idea was actually to scale down the things, make it very small and extremely cost effective. So that's how we started this whole thing. And myself and Satyanarayana was mainly involved in this work. So this is a kind of history. Like 2005, we had this box with a desktop computer. And here you can see that's a big metal box, which is the size. You can see the width is more or less same as something like a 15-inch monitor. So, and one more thing is initially when it started, we had no concept of actually going for a manufacturing or anything. I remember the first demo was given in Delhi University. And after the demo, some 2 or 3 teachers from Haryana, they came and asked where can we buy it. The only reply I could give was actually all the details are available, so you can make them. The circuit schematic, all the things were. But we soon realized that it is not going to work out that way. Then we found somebody in Delhi to manufacture them, on a very small scale. And this parallel port was vanishing. Then we just went for a serial port version. So here at this point, we just changed, the design and started using microcontroller. So it became something like a communication between the PC and this unit. So, and that design still we continue. Like it was a kind of job division, basically. And today, when we look back, we think that is a kind of, good decision, because all the real-time measurements are taken by the microcontroller sitting inside the box. And it simply obeys the commands coming from the PC. So then we continue with this design. From here, this serial port version had a DC power supply. So we had to go with it, something like a 9-volt adapter. So then we found that this 9-volt adapter is becoming a problem. And I'll explain you the problem is, somebody reported all the ADC values are coming wrong. And then later on, we realized that the AC supply, which is supposed to be 230, was going down to 150 and all. So the regulated 5-volt goes down because of the DC adapter. So once we realized that issue, and in 2010, it is not 2011, first time we made a design which is based on, it's a USB powered one. That was first time called. So again, this confusing name, I should explain how it came. The first thing, we call it as Phoenix. That was actually Physics with Homemade Equipment and Innovative Experiments. Acronym for that was called Phoenix. And when we came with this device, we thought we'll change that and put another name for the device. And the Phoenix is now the name of the project. So actually, we decided to call it as Experiments for Young Engineers and Scientists. So the acronym is actually just ICE. And then I decided, okay, I'll give the acronym ICE. Then another collaborator, we had a strong collaborator from France, George, is a Debian developer and a school teacher. He told, don't give anything which is having a meaning, because Google search will give you all kinds of things. So we gave a meaningless name, XPICE, that is taking 4 letters from the experiments, and then Young Engineers and Scientists. That's how this acronym is given. So we call it as XPICE. And once this device came, and with this, we had some interaction with the Ministry of Education. And that time, the HRD Ministry Secretary, he said, why don't we make it something much cheaper? So that was just a suggestion. Then we just made another one, which is smaller, and but it became actually slightly better than this one. That was XPICE Junior. And that was in 2012. And another thing with this project was, you can see that 2005, 2006, then we don't do anything for 3 years. No new design, because all these things were done during our free time from other accelerator related work. So from these 3 years, the other things were, we were quite busy. So things were not happening on this side. But in this 2012, we made this. After that, IUAC, we did not really put effort to make new devices because our high current injector work was picking up and we were quite busy with that and many other reasons. And this XY17 came later on when Jitin, my other son, so he started working on developing a new unit. So he made something called CLab around 2016, which was with a built-in computer and all. But then we got something made with a scaled-down version of that, and we called this. So he called it as something like CLab Junior at that time. So IUAC, we took up that design and we called it as XY70. So this is our major, most advanced unit because it's far better than this one. I'll just explain it. And this latest entry is in the last year, 2002, it is CLab 3. But this is basically only the form factor is different. Otherwise, it's more or less same. Some little bit of some additional features are given into this. And this is a very, very small device, actually. It's extremely small. Like you can put in the shirt pocket, this one. So that is you can say the history of this project. And now if you ask what is this device, you can say it's middle CLab 3 is here. It is something like combining a DC supply, oscilloscope, frequency counter, a manometer, data logger, capacitance meter. So everything you just try to squeeze into a small box. So of course, compromises are made. When I talk about the oscilloscope, it's basically, you can say 3 megasamples per second for channel. So it's not something which goes in gigasamples, but it works in megasamples. But the reality is most of our lab experiments, we work in audio frequency kilohertz range. So that perfectly fits the bill. And DC supplies, of course, it gives you something like plus minus 5 volt DC supply for doing, say, diode, transistor, or experiments. But the current is again very limited. And that is that earlier we thought it's having a very small current capability, but later on we realized it's a good thing because this XY17, this unit, it has thousands of pieces. Like in Kerala itself, there are something like 2,000-3,000 pieces were there in the higher secondary schools. And last year we had actually before COVID, they acquired all those things and kept ready, but the training got delayed. And last year only, we conducted the training around 2,000 teachers. It was a massive effort. But we found all these units which we started using it for the training, and none of them gave any trouble. And one main reason is making a short circuit or any other things doesn't spoil it because its current capability is small. It's only 5-10 milliamperes. So all the experiments, so it's a kind of low current affair. So to summarize, if you ask what is this device, you can say a low cost device that can say from so in engineer's point of view, if I just look at it, it's like, if you can see, it's a scaled down version of the particle accelerator control system. There we have a couple of thousand signals. Here we have only 10-15 signals. So it's if you look at generically, it can generate voltages as a function of time. And it can also read voltages as a function of time. So that is its capability. And with the help of software, you make it a tool for learning by exploring. So it just see this feature like measuring voltages and generating voltages as a function of time. See, when I say generate voltage as a function of time means it becomes a function generator. You can make an arbitrary waveform and all those things. So now with the help of software, that becomes function generator, oscilloscope, other things. Now, and one important point is all open software and hardware. So it's all distributed under free software licenses, and hardware we have put under CERN open hardware license. And basically there are two objectives which we had in mind right from the beginning. And one was actually to reduce the total cost of ownership. That means it is not the cost of the device. You also need a computer to operate it. So you have to add that. So for that purpose, what we did was we just started, tested with the Raspberry Pi. That was a low-cost single board computer. And also we tried to run it with the Akash tablet. That time when the HRD ministry was promoting it. So that means the total cost, becomes low. But the ultimate thing now happened because in 2022, 2 years back, when Jitin came up with the Android version, so that the mobile phone, so that means you can say that total cost of ownership has become just the cost of the device, because phone is now almost available with everyone, including the students. And the second point was enable the teachers to develop new experiments rather than just giving a set of pre-designed experiments. So the best we could do earlier was give a Python library and write small Python programs. How to basically, if you see a science experiment, what we perform in the lab is it is just reading some parameters and controlling some physical parameters. Like you may read a temperature, voltage, current, or anything, or velocity, anything. Or you may control something like a pressure, temperature, or voltage. And it is all happening in a predefined sequence. For example, say cooling curve experiment. You control the temperature of a heater, or you switch on the heater to make the water temperature something like 100 degrees. Then you keep on measuring the temperature. So that process is happening as a function of time. So this sequence we control in software. So Python is something it's a language which is easy to use. So we just went for that. But here also, ultimately now what has happened is the Android version supports the visual programming, like the drag and drop programming, like you will just assemble a program using the building blocks. So we'll just see how that is done. And so this is the visual programming thing. You can see these blocks here and how you can do experiments. So like dragging 2-3 blocks, you can make an oscilloscope, or if you want to do a data log or everything, you can code using it. So these two objectives are now more or less met. One is making the total cost of ownership much, smaller, and also making, development of new experiments at the user level. And this is what is inside the hardware, one page of it. There's one more page. So this is on the website. The design is open, this actually. And giving few names, but doesn't mean that the only people. There's a large number of other people from the academic community who contributed. And this few names I mentioned because Pramod he joined the thing in 2005. And that time I was doing everything in C language, and even graphical user interface, oscilloscope, everything was in C language. So somehow I met this person, online only. He had some article he wrote in the Linux for You magazine that was about the real-time Linux. So then I asked him whether he wanted to collaborate. So he just took that first Phoenix box, that metal box. And what he did was he converted my C programs into Python. So showed that it is much better to use Python. So basically, I didn't know Python at that time. So he more or less, he can force me to learn Python. And the next version onwards, it has been Python only on the PC side. And microcontroller side, of course, it is C. And Dr. Ambar Chatterjee was also contributing on the Windows version of this earlier, Spice Junior. He retired as the head of the Nuclear Physics Division in BRC. And then Praveen Patil is in the college in Belgaum, is teaching there. And Jitin basically he started contributing with his XY17 hardware, and later on, and nowadays mostly the development he is carrying forward. So he is now at present he is at Calcutta University as a postdoc. And George Kasnadar, he has been there right from the beginning, 2006 onwards. And he is the person who first took this, you can see around 30-40 boxes, and he tried the method of giving it as a homework. So he just trained his basically higher secondary students how to use it, and they take it home and give assignment to perform experiments and bring the back, back. So that's a kind of, like giving it like a library book. So this was the kind of new ideas. And other than this, there are a lot of people were there, like I would like to mention like Dr. Professor Raibacker from Pune University, now retired. So he is the person who was instrumental in putting this in the BSc syllabus of Pune University. That was again in 2010 or something like that. And many people, Professor Nagarajan of CBS, and Professor Ashok Thakur, and Professor B.N. Das in West Bengal. So, I mean, there are hundreds of people, and not only these people, whoever attended the program at IUAC used to conduct every 6 months, 1 week training program. So every program there used to be suggestions. So that's how it grew, something like 5 experiments because of the suggestions from, people. So now it has maybe 100 experiments are there. So it has been a collective effort. That's what I like to mention. And now probably we can just try some experiments also. Before that, I'll show on the website some experiments, or before going to demo, maybe we can just mention something which is related to this. Not only these experiments, we were also doing something on like nuclear physics experiments, and the focus was like nuclear physics experiments were done at very few places, and basically it was going down. And one reason was basically you can say there are 2 reasons. One is lack of equipment, like only GM counter was available. There's nothing like spectrometer, like alpha or gamma spectrometers were not available. They had to be imported and expensive. But another major issue was the source, availability of radioactive source. Gamma sources were available, but alpha sources were not available to colleges or universities, because it needs a radiation safety officer, because the sources alpha sources are not sealed, they are open. So here we tried to do something with this thorium nitrate powder. So you can see this spectrum was from the powder, and this is the thorium decay chain. And it has actually, in the chain, it has all these alpha 4, 5.5, all these alpha energies are there, up to 9 MeV. But everything is made out because it's a kind of powder. So self-absorption makes it, all the peaks will be like broadened. So then we made a unit as long back. The Phoenix, you can see a small attachment and chamber. And we could not do it, but another person, because everything was on the website. One person from Germany, he ordered it, and he sent me a spectrum like this, and it had all the clear alpha peaks. And he also told me how it is done, like doing an electrolysis using copper electrode. And but when I tried to do that, I could not do that. I could not get the results. But then later on, Professor Devinder Mehta from Punjab University, he gave me some lead electrodes, and some thorium nitrate was available from the market, from the lab suppliers. So what we could get was, first we didn't understand what it is, but when we saw the peaks, and we could realize what we were getting was actually bismuth 212. And this bismuth 212, you can see that it takes 2 paths going to the lead here, like bismuth to polonium and bismuth to thallium, these 2. So here, what we get is something like, say, 9 MeV and a 6.2 MeV peak. And the data, the literature says the path is actually 64:36 ratio. So we could verify that. And the beauty was that actually, not that actually, it's like it's having a 1 hour half-life. So you can never see like we know that radioactive decay, the source is gradually decaying, but whatever sources we buy, we cannot observe it because its half-life is large, and you cannot never buy a 1 hour half-life thing. By the time you get it, it's all gone. So this prepared source, we could just plot the number of counts, count rate as a function of time and fit it exponentially and get the time. I could get actually 72 minutes. The actual is 60 minutes. So this later on, actually, Jitin, his company is his part. So he made some units which with a much better chamber and all those things, vacuum system and all. You can see it here, this alpha thing. And so another thing I just wanted to mention before we go to these demo and the things, like it was actually an overall picture, like how to couple this theory, modeling, and experiment, and everything. And the common thread is actually Python. So using Python, what I would say when physics and mathematics, I mean, we should make Python compulsory. Because if you want to do any scientific computation, that's the best choice. So here we can do this theoretical computation, modeling, simulation all in Python. And also with this box, you can collect experimental data also using Python. And here analysis, visualization also. Just because of this reason, so this is another experiment, like, this small Python program is simulating that tool like a spirograph. So whatever patterns we used to do with this tool, you can generate it. So we will just try some examples for it. So all this information I have put in this scicchool.in. There you can download the Python book where all these examples are given. And also in the website you will find, so I'll also mention what I am doing at present. I'm just finishing something like, you can go to this scicchool.in and find OpenQP. This is basically make a question bank and generate question papers for exam. So that such systems will take away, I mean, a lot of effort which teachers have to do to prepare question papers for exams and also. So that kind of monotonous jobs can be easily automated. It's again an open source thing. So now let us go back to our this portion. We'll try some experiments. So let me just close this one. And there's so many things. So this is the XPICE website. So here you can see the experiments are like different levels. So getting started, some small activities, then school level, and then electrical. So let me just pick something, which is interesting. So I go to the electrical section and suppose, say, if you pick an experiment, this one, simple LCR circuit. And this theory we teach, but when it comes to experiment, normally it's difficult to do, because when you talk about a transient response, suppose I take a small, something like a 0.1 microfarad capacitor and an inductor, and the step response which happens within a millisecond, it's over. So you have to collect the data. So after applying a step voltage, within millisecond, you have to take maybe 100 readings. So that's difficult. And if you see on the internet, this particular experiment is there in the syllabus of most of the universities abroad. And how they do is they take a square wave generator and a digital storage oscilloscope. So every step of the rising and falling edge of this will generate a ringing, and that is captured using a digital storage oscilloscope and analyzed. But we can do it in a much easier way. You can see here the photograph, what we have put the inductor and the capacitor and 3 wires. So here we apply a step and one side is ground, and on this channel we'll get the so I think I have to stop screen share if I want to show the camera, right? So can you see my camera feed now? Hello?
No.
Camera
Only okay, I think I have to remove the screen share for that probably, right? Stop share, okay. So, okay. So now, okay, at least I can. So you can see here, right?
Now you can see.
Right. So this is the setup which I'm going to use. We have the inductor, that black thing, and a small capacitor sitting there. So then now how to do that? So let me just start screen share. So I'll try to do it in a different ways, screen share. Let me just first we'll use the graphical user interface of XPICE.
Most of the time you people are learning about the graphical GPU, graphical user interface, GUI.
So I'm just sharing that GUI, so you can see that GUI right there.
Yes, sir.
Yeah. So okay. So here, so part of it is here. So I go to electrical and I have the RLC transient response. So it also has a online, help and all. It will show you the picture and all. But now here I can just give a step. So let me clear traces. So I give a 5 volt 0 volt step. Can you see this ringing here?
Yeah. Yes, sir.
Okay. So this is our experimental result actually. So what we have done is all we had an LC. R is not connected. R, you can say this resistance of the coil, something like 10 or 20 ohms. That is R. And if you want to change the damping, you can put series resistance and try again. So here it is clearly an underdamped case. It is oscillating. So you can analyze this data by fitting it with the equation, which is sine multiplied by exponent. So then it says it is 5.8 kilohertz and damping factor is 0.0.
Do you know what my teacher, my sir told? Either they are offering us 40,000 or 50,000, so we must go there. Leave it. There is no need of going there. It's comfortable to earn this much of money here at our school. You must sit along with your parents.
So now, same thing. Suppose say this GUI which we give, but you say without GUI also we should be able to do that. Now, I stop this pair and let me just share another window now. So what I'm going to share is actually what is happening. Okay. So you can see a window there, right?
Visible.
Yeah. So let me just close the graphical user interface, other one. Okay, so here there is a small Python program, right? So basically this program which came when I just clicked on this website, where it is all documented. So all the Python programs are given there. So I just brought that. So you can see here, is it readable? Is it readable?
Yes.
Yes, sir.
Okay. So first line, you can see the importing this module and then connecting to the device. And we say we take 500 readings and the time between two reading is 2 microseconds. And all we do is actually, we just connected the output, digital output to the inductor, one end of the inductor. That we set to 5 volt and waited for some time so that it settles there. And then there is just one call, just capture A1 with an action of setting low on our OD1. Okay. So
How?
now let me just run this and see what happens. Oh, there is a catch. It has given the output, but that screen is not shared. So let me just show the output.
The Python section. They will be able to.
Can you see that now, that graph?
Yes. Yes, sir.
Right? Yeah, because I'm sharing the entire desktop. So here, the same experiment we do with something like, Python lines of Python code. So here things are very clear. So this graph is given and also the data is saved into this file, lcr.csv. So you can take it later on and do further analysis. Like you can do that mathematical fit and everything. So that can be given as an exercise to students. So the basically the idea is actually, see, we convert every experiment into a kind of, to use the methods used in the research. Like you acquire data, then you mathematically fit it into a model and extract some parameters. That's what is happening here. We fit the that ringing that output curve and fit it with the equation and extract the frequency and the damping factor. And this is actually a kind of common, practice in any experiment when you go to the research. So another thing is a small experiment what you can do is like gravity by time of flight. It's you can say the simplest possible experiment. That is, I think the camera is still on, right? Or should we, maybe I stop share and, okay, now it's there, right?
Yes, sir.
Yes.
So now let me explain what is there. This is, it's nothing but a selfie stick. So we asked to make an equipment which is, so let me just show you what it is. It's a selfie stick. And selfie stick, it is, pasted a small relay. Relay is electromagnet. You buy a relay, cut that and use that electromagnet inside the relay. So you can get this relay online. It's something like 50 rupees. You can buy this. And actually, you don't need the selfie stick or anything. You can just connect, put it anywhere. And other thing is, like, you have to have two pieces of maybe razor blade or something. You can see here that cross, right? So two strips, metal strips, spring-like, right?
Yes.
So if something falls on it, it make a contact. That's all, the whole thing. Nothing else is there. So now, what we have to do is we just have to hold something here. So let me just start that program once again with UIF and run it. Are you seeing the device now? I mean, the camera feed?
Yes, sir.
Huh? But not the code, right? Yeah, screen share. I'll enable the screen share. Yes, screen. Yeah, so the code is again visible right here.
Yes,
visible.
Yes, sir.
The Python code, right? So this Python code, if you look at it, so S is the distance, height. So height, I think what I have put the height at roughly 20 centimeters. So that's 5.20. So now the code is set state OD1 to 0. And the relay is actually inverted logic. So if you put the OD1 0, the magnet is energized and the MS ball is sitting there. You could see that, right? The MS ball is hanging there from the camera when the camera feed was on.
Yes, sir.
Okay, so now the code says you just press the enter key, then it will put the set to archive this function called. One line of Python code it will execute. So let me go here and try to do that. Okay, press enter. So it fell down and it said 0.2 seconds and the calculated G is 9.9. So mainly because the height is too small and the error will be high. So let me repeat it once again. Yes, 9.86. Right? So, and this experiment, it's conceptually extremely simple, right? I mean, there is nothing to think about the theory. You just use S is equal to half gt square, and 2s by t square will give you the value of g, the direct measurement. And another thing about this experiment is, like, even without assuming that S is equal to half gt square, that you can do it. Suppose, say, you do it 100 times with the different heights, like a 5 centimeter, 10 centimeters, say up to 1 meter. So you have something like maybe 10 or 20 values. So all I have to do is now I do a mathematical fit. And suppose, say, I have two parameters. One is the height and other is the time of flight. And I suppose, say, assume that I have no idea about the nature of this relation. What is the relation between the time of flight and the height? So I just do a fit. See, when you don't know the relation between two parameters, people normally do a polynomial fit. Suppose I use ax square plus bx plus c and fit the height and the time. So what you get is actually x square, right? And that parameter a will be g by 2. And you can also see that the distance and the second derivative is actually acceleration. So you can see a lot of correlations. Just blindly, rather than blindly putting the equation, you can see how things emerge when you analyze the data. And another thing is, when I just want to mention is, one student came and did this experiment meticulously, and he made the measurements, put the wrong values, because instead of, see, when you measure the height, it should be measured from the bottom of the metal ball, because this point is coming and touching here. So he measured from the center of the ball and analyzed all the data, but doesn't affect your result, because that goes into it doesn't come to the the coefficient of x square. It goes into the constant. So one can learn many things, in experiment by doing such things. And maybe now we can just pick up another one that is something which we do all the time. Can you see that? There's a transistor there. So let me just share screen and show what experiment we are on. You can see something. Our graphical user interface came and told I don't find the device, because the other Python program was still holding it. So I have to just say device recommend. There's only one program should access it at a time. Right. Let's skip that program. Okay, so we have our GUI ready. So go to electronics, and what I've taken is the transistor characteristic. So here, before going into that, let us just have a look at it from the website. So everything is there on the website. So just, you can see the browser, right? Hello?
Yeah.
Okay, so I just choose the experiment. And here it says, see, this is all we have to do. I mean, nothing else. We have to connect. Let us see how it works, first of all. See, what we want to do is, like, we want to find the relation between, suppose, say, VC and IC, or IC and IB, or such things. Everything, this is common. So what we do is, we apply a voltage here, and that is basically VCC, and we measure this voltage. So when you know both of these things, you know the current, because this resistance is known. So once I measure A1, I get the IC, VC and IC both, because A1 gives me VC, PV1 minus A1 divided by 1K gives me the IC. So I can change this from 0 to 5 volt and take reading, so that I get a set of VC versus IC. But there I can set the base current, so that the graph, I'll get a family of curves. So here, this is the circuit. You can see that 5 wires and 2 resistors, and the transistor is sitting here. It's a very simple setup. So with that setup, we come here, and first we said, okay, voltage at the base through 100K, we set 1 volt. We got one graph. So now I make it 1.2, and I get another graph. So I can get a family of curves very easily. Oh, I made a mistake there. I think 1.5, I put 15, Yes. It should have done the error checking. 15 is not allowed anywhere. Okay. So It is quite simple. But here also, if you want to really know what is happening, we should take the Python route actually, if you want to really go deeper into that. So what we should do is we should go to the experiment, this page here. So here program Python program to generate VCIC plot. So that my setting is that it will automatically open with this Genie. So my GUI is not there. So let me just, so here I'm putting this, the collector resistance is 1 kilo ohm. All this information is put in the program. Base resistance is 100K. So now first thing we do is set some base current and open a file, and in a loop here, see collector voltage 0.1 to 5 volt. We go in a loop and let us run it and see what happens. You can see the graph coming, the points are plotted like this. So the difference between this and the GUI method is GUI gives you the output characteristic. But suppose if I want the base current versus collector current, GUI is not written for that. But if you want to do that, you can just go here and say program to plot IB versus this. Here it is, this one. Let us try to run this. You can see it's a linear curve. And this slope from here, you can get the gain, current gain of the alpha of the transistor. So these are the kind of, the things which we can do, and what all you can do, it is given here. And now probably we should see how we can use it with the phone. So we can connect this whole thing, the device to a phone and use it. So probably I'll. Jitin? Huh? Oh, just which experiment? Like first, which experiment? Sensors. So first of all, let me just. I'll just give an overview and then. Arila. So I just put an OTG cable, and so here normally, see from here, if you see this goes to the PC, so that it's anyway, if you put a pen drive or something to this phone, you have to use OTG cable. So same way it is connected. So we can repeat this transistor experiment with this basically. Let me just I'll do this, and then Jitin can show some experiment using this I2C sensors for pressure and all those things. So here it is. So let me. So I'm starting to broadcast this screen of my phone, so that is much easier. 192.168. 141. So can you see my phone screen there?
No.
Hello?
No.
No.
Oh, okay. I have to share the screen. Okay. So where is Zoom? Share. So our hardware connection is same. So let me just share the screen now. Now it's visible, right?
Yes.
Yeah, visible.
Okay. So from here, I start this application, and from my phone, I have to enable the OTG. Additional settings. OTG enabled. So then it asks for permission to connect the device. Android works like that. Okay, so here you can see there is experiment section. So it is divided into, say, getting started. Like in the website, it's divided. So school level, electrical, like that. So we have to go to electronics section. And electronics section, if I just move to NPN transistor output characteristics, so I get this. So here in the phone, all this help is given, diagram, everything is given. So now here I can see it. So you can see that 1 volt is set here. So here you can manually change by sliding, putting a slider. So you can see the graph, single point graph is moving when by hand I am changing this slider. So that is just to manually, make sure everything is fine. But then you go to the record data tab, then you can see that base voltage through at 100K is 1 volt. So I can just say now ramp is from 0 to 5 volt, right? So here if I tap, I can just make this to say 1.2 and another one. So here, see the major advantage is this graph. It is not this picture we are not interested. Suppose I say now share this CSV data. Whosoever in that May 24 group created by Satya, so they will get the CSV file, right? So with this CSV file, you can just, take it to your computer and plot the things and all. Okay. So similarly, all the experiments which we do with the PC, it can be done from here. And some of the things are slightly better here, especially the school level thing, which is, our PC software is a bit lagging because it was done in 2017-18 that time. So here, basically this section was written after some discussions, long discussion with the higher secondary teachers. So what they wanted was basically give an introduction to electricity in a very systematic manner. So I'll just, how much is time? Okay. So our time is almost up to, hello?
Yes, sir.
At what time we should stop?
How much time you need actually, sir? Can you just give an idea how much time you need?
No, it's all flexible. So if you have an endpoint, we can just,
So maybe we can wind up it in another 10 minutes.
Yeah. So then what we'll do is I'll ask Jitin to do some, how to use the other sensors, that. So Jitin. Oh. So I'll stop share. So he'll show some,
Okay, sir.
Hello. So I'm here. Can the host please broadcast my screen.
Within you have to share screen, no? Right?
No, just my video will be, my video shows everything.
Yeah,
But
it is
here
visible.
the-
Nitin.
My
Huh?
video is visible. Can you?
Yes, visible. Your screen is visible.
Oh, okay. Now it's here. So I have to make that. How to make that big?
You have to mute your video, otherwise it will keep taking over. So is my screen visible?
Yes, sir.
Yes.
Yeah, okay. So I have been working on the Android app, and I'll just briefly show what it can do to make this a really portable sort of setup. So right now I have the transistor CE set up on this device here. So you can see the transistors there, the resistors and all. And the app is broadly classified into, well, first off, you have the oscilloscope, where you can, let's say I want to measure a waveform. So I've taken the waveform from WG and just connecting it to A1, and you can see the waveform there. I hope you can see it. And the usual oscilloscope stuff like time base is here. You can have single channel mode. You can change the trigger levels. And you can also analyze data. For example, if I want to know the frequency of this data, it's easy to just fit it. And you can see the frequency here is 1000 hertz. And there's a particular amplitude and phase associated with it. And all the other controls are here. Now in the experiment section, you have, well, various experiments. So if I wanted to look at transistor CE, which is here, so I have an NPN transistor connected. So I can just go here and NPN transistor output characteristics. And here, this allows me to set the base voltage, thereby the base current. And using this PV1 voltage, I can actually trace out the graph. Okay, so my circuit is complete. I just moved it to put the to visualize the sine wave. So obviously I'll get wrong readings. But yeah, so now I have the plateau showing up for a particular base current. And the record section allows you to get systematic readings for each. So there's about like maybe 70, 80 or 100 experiments classified into broad categories. So having an app on your phone allows you to just done. What? Just done already. Yeah, okay. So allows you to like carry it out. Anyway, so now speaking of extending the abilities of this instrument, there are several sensors on the market for measuring various parameters which you commonly use in physics labs. For example, luminosity, magnetic fields, humidity, etc. So I have a small list of sensors here. Are you able to see a list here?
No, I mean, where is the list? I
Can you
mean, I'm
see?
not able to see. No, I'm not able to see.
What are you currently looking at?
I mean,
we are able to see
getting-
three of screens. You are in one side corner, then C lab 3, and then it's showing the getting started school level electrical, electronics, mechanics, that thing.
Yeah, this thing.
Okay, so my slideshow has not been, 1 second. Can we just do a screen share from the
Yeah, you haven't shared your
Zoom
screen
interface?
yet. These are
Okay.
say 2 cameras and one your mobile screen. Your laptop screen is not being shared.
Correct. 1 second. I need permissions for screen sharing actually. It says host disabled. Could you please just activate screen sharing for me?
Yes. Just
Share.
yeah, now you can share.
So I think you should be looking at a list of sensors now.
Yes.
Yeah, now it's Now there are.
Okay,
Yes.
so I have some slides here. So like I said, there are several sensors in the market for everything from pressure, humidity. There's a whole list here. And what I've basically done is, since these typically cost very little, like 200 rupees, 300 rupees in that range, but you need to write some code to extract data from it. But all that has been taken care of here. You just need to make the connections. Typically, there are only 2 communication lines and there's a power supply and ground. So 4 wires need to be hooked up to get data from any of these commercially available sensors. So I'll just go back to my video link and share how to use one of these sensors. So I hope there's 3 screens now, right? Okay, so what I have plugged in here with this single wire is a pressure and humidity and temperature sensor. So it's called the BME280 and costs about 250 rupees on the market. So what this measures is all 3 parameters. Now, how you would use it with this instrument is to go to the data logger. Now, the data logger gives you options to pick a particular sensor. So now it's automatically detected that this particular sensor with these parameters is plugged in. And also on the board, I have plugged in another sensor, which is a distance sensor. I'll get to that after this. So let me see. If I want to look at pressure. So it says pressure is 1.01 bar. I hope you're able to see this.
Yes.
Right. Okay. So it says pressure is 1.01 bar. Now, if I were to physically increase this, you can see the pressure go up. But more interesting thing is, I'm getting a lot of noise from some other microphone. I'm sorry. Anyway, so the interesting thing is, in high schools, we teach that, as you go up into the hills, the air pressure drops. But to actually show it in a class, it's possible with this sensor. So I'm going to record this as a function of time, just say start. And now as I pick this up and take it, to a height, you can see the pressure drop, right? I hope the graph is visible.
Yes.
Can I get some
yes.
feedback? Is the graph?
Yes, yes.
Yeah.
Yeah. So, and now as I take it near the floor, you can see the pressure climb, right? So a sensor that costs as little can be used for simply demonstrating that, atmospheric pressure is a function of altitude. And for every 8 meters that you go up, near the sea level, every 8 meters, 1 millibar of pressure drops. So when we conduct workshops, students typically pick up this sensor, their phone, and the device, and then they walk up, to different floors. And we ask them to note down what pressure exists at each floor. And from that, it's about half a millibar per floor. So they can say that, yeah, every floor is 4 meters in altitude, in height. So, it's a practical application of this particular phenomenon. And I'll just show one more sensor, maybe 1 or 2. So there's one already on the board. And visual coding. Okay. So there's one more sensor. This is sensor with visual coding. Yeah. Okay. So there is one more sensor here. This is called the VL53L0X. Again, 200, 300 rupees. What it's useful for is measuring distance. So it emits a small laser pulse, and on the screen, I can actually see my camera pick up that small pulse. And if there is an object oscillating on top of it, you can see the distance move. Can you see that little gauge move? I'll start the graph, makes it more clear. So now you can see that as this oscillates, it's picking up readings. So I can use my hand also. So assuming that this is a mass spring system and you want to accurately calculate what the time period is, you could use this sensor. And in the data logger, you have your analysis functions. So I'll use SignFit and just select a particular region. And now you can see that the frequency is 0.666 hertz. It's 666 milli. There's a milli prefix here. So it's 0.6 hertz with which I was oscillating that particular body, particular object. So this actually becomes very useful to, track the oscillations of a pendulum or a mass spring system. And especially because it uses light. The other alternative is a sound-based sensor. But when the sound-based sensor encounters spherical objects or soft objects, the sound does not reflect back. So that creates problems. You get a lot of missing data points. But with this, it's a small laser pulse. So as long as your object is light colored, it will simply pick up these signals. So now, I'll go to visual coding and show you a small bit of code on how to use visual coding. So in visual coding, I'll go to the sensor add-ons section. It's a very simple piece of code, which will, yeah. So now in visual coding, on the left, you have all these coding, well, blocks. These are all functions which serve various purposes. And under the XPy section, you have a lot of blocks for getting data, right? So now let me connect a particular sensor. So I have a magnetic field is here. Okay, so it's a magnetic field here. So first step is you need to check which sensor is connected. So there's a scan button here, which automatically tells you, okay, there is this sensor called HMC5883L, and it measures magnetic field along X, Y, and Z directions. So let me just use the default X, and it's very sensitive. So it measures Earth's field. As I spin it around, you can see it. Now this block is connected to another block called plot. So this plots Y versus time. So it's just a time series. And there is a loop which encloses this whole thing. So it will continuously plot. Now, if I run this program, you can see that it's plotting magnetic field values. As I spin this, I can just show you my screen only. So you see this magnetic field values. Now, I don't have a magnet here, but if I take it near, let's say, a speaker, you can see the magnetic field shoot up. Right? So this is my headphones are, well, they have magnets in them because it's a speaker. So you can see the magnetic field shoot up, but otherwise it's the Earth's magnetic field. So I think that's all I wanted to show. I think the host can take over.
Thank you. Thank you, Dr. Jiten. Yeah. So
now I'll just one more thing I want to show. I mean, that is, I mean, not about this device or anything. That is about the actions. Can you yeah, here. Can you see the screen now?
yeah, yes, sir.
Okay, just wanted to mention these activities. So here there is a page in the resources 2-day workshops. So I just wanted to tell, I mean, this is the kind of, in which we want to pursue. So this gives a scheme of a 2-day workshop, how it is, what are the things covered and everything, what are the requirements and all. And these kind of things which already, I mean, some are entered, many have been conducted. That is by this APT Kerala. So I have been doing this, starting from, last October.
Okay.
So here, how it goes, we can, like it's done in an ordinary classroom where the bench and desk and all are there. You can see here, right? So it's all, 2 people sharing and practicing it. Huh? So that way one can give a hands-on training to something like a 40-50 participants. That's quite easily that can be done. So the reason for showing this is just in case if anyone interested in pursuing it, so we can, we can take it up. So I hope more or less
Yes.
covered. I think time is already
Lots of
exceeding. So now I just wind up. Thank you.
Yeah. So over to Professor Sejwani.
Yeah. Sapna, see, the problem is there is some setting problem. The
Right.
chats are coming to me only.
Right.
But
So
there are not many questions. They have just appreciated the session. I think only
Okay.
Professor Sejwani has asked what is the cost of CLAB 3.0. Anyway, he is going to take. Yeah. Yeah.
Okay.
Kuladip Kumar says a very informative talk.
Yeah. In fact,
So,
it was.
all of us are interested in knowing what is the cost of CLAB.
Cost at the moment is actually 3,800 plus tax. And tax is
600
quite
plus tax only.
It's 18%.
Only 600 plus tax.
No, 3,800, 3.8.
3,800.
3,800. So it means that roughly
It's not too much.
4,000.
Below 5.
No, 18% means roughly it's close to 5, right?
It's
Something like,
5,000. Okay.
Yeah, close to 5. Yeah. And there are other, slightly costlier models, which is actually put in a wooden box and out for lab use. And that is some people like, some, especially colleges, they say they want something to be kept on the table, slightly bigger one. So a new design was, but functionally the same thing. Only thing is the same connectors have been taken to a binding post and all, so that and one reason is very small things, which can be put in a pocket. It's very difficult for colleges to keep it. So, chances of getting misplaced and all.
And sir, my question is that when you conduct these workshops in schools or colleges, so do you provide them these kits, or the college or school have to buy themselves?
Whatever these programs which I conducted, that in my trolley bag I can easily carry 20 of them, because it's something like this. Actually, if I put this, can you see this?
Yes, not exactly.
Yes, there was a wire actually.
My camera, let me just see if I see my.
Let me pin it. Maybe I. No,
Yeah, you can carry easily 50 kits, like 50
20
mobiles.
20 goes in a very, very easily in a trolley bag. So I used to carry this, because this has not only the box, some accessories, everything in that, put in a plastic box. So something like this. So that's how it has been done. But most of these colleges, they had their kits also.
All right.
So we had some extra, but this, like 40 participants means we need 20 kits. So that I was, carrying with myself. So that may be another round if, there is enough interest, one could, manage. So it is.
Yes.
Baba is still there. Baba Sudar, still listening? Hello?
Hello.
From Ratnagiri, we had some programs there, and I think he's not there.
Recently, we used these kits for NGP exam.
Yeah.
It was conducted. Yeah. Last month, it was conducted in Delhi for our gold medalist. One of the experiments was on that. Satya, the coordinator there. Excellent feedback.
Right, sir. Wonderful talk.
Thank you. Yeah.
In fact, we gave 5 kits to the 5 gold medalists, madam, from IAPT.
Yeah, I know that it was there in IAPT group.
Yeah,
it was shared in IAPT group also. Yes.
It was in great demand.
Right.
Thank
So
you.
last year also, the students who are selected for International Olympiad, 5 students, the IPHO, they were given these kits, X5s, in Home Baba said. Yeah. So it's becoming a very popular kit now.
Very attractive. And now using mobile, they can do
mobiles. Yeah. So it's
Thank you so much. Actually,
very good connectivity.
Yes.
And sharing is
because
easy.
The University of Calicut, now their 4-year UG, they have put these experiments in the syllabus.
Great.
The 4-year UG. So they send me a copy. So many of them they have included in the syllabus now. The main reason is very easy to conduct. There's not much of a financial implication.
In our college also, we have been using for a very long time. And when the students are able to compare this with the conventional experiment, the joy on their face is really amazing. So thanks to you for such an invaluable contribution. That has been very nice. Thank you.
Thank you, Dr. Ajith. I am a lover of the experiments, and whatever you have designed is a wonderful thing. I don't know why I didn't know about this thing. I want that this type of the workshop by you should be organized for RC01 also. So I think I will talk to the president of my RC01 to organize such a wonderful experimentation. I saw all the experiments. Of course, you have done all of these on Python, but I have developed some examples, say experiments, but not with the device and wonderful device and made by you. But I have done work on the Arduino. ठीक है ना? So Arduino language is very simple. It's simpler than the Python, but as a lover of experiments, I love your this device, and I think I will purchase it. From where can I purchase? And you just
Okay,
let me know.
yeah, xspice.in, you will find that how to buy, that hardware availability on page is there.
And what is the website of this? What is the name of it?
xspice.in, xspice.in.
Okay.
xspice.in.
So thank you very much, and I really love it, Chicken, and it was a wonderful talk, nicely explained. All the experiments were shown very nicely. The gravity experiment and the other experiments, and you have also developed certain experiments for the school level, for BSc level, for others. It's a wonderful thing. I will go to this site and see what experiments I can perform on this. Can these be performed on the online also? Can these be experiments?
No, it's all with no, not online actually. See, we tried all those things, connecting this device to a server and all, but see, basically making the connections oneself and
okay,
that virtual experiments, virtual labs, we tried it out, but we don't see much of a point because you have the device in front of you and just make the connection. So that feel the online ones are not really.
It should be interactive.
Yeah, correct.
We normally call it as the freedom to make mistakes. Just make a wrong connection, nothing comes, then fine.
Yeah,
correct it. So with online, you never can make a mistake. Actually, it's always you are on the right path.
After purchasing this device, and if I have some sensors, can I use those sensors with this device?
Yeah, the I2C sensors, you can straight away plug it. That's what it was showing, right? Just you take the device and there is a 4 wires, that thing you just plug in and automatically it will detect the Android software. So Android is much easier to start because on the PC, the installation, all hassles are there. But there, the Play Store, you just get the app and, get going. And the beauty is the data can be transferred by email or something to your computer. Suppose you take the characteristic curve, you can get in the computer plotting and further analysis. So it's that way it's useful.
Sir,
Thank you.
Just a minute. Can you share your email because someone has asked?
Yeah.
Thank you very much, sir. How can one approach for teacher training program?
Yeah. Just I'll just share the screen once again. So this is the xspice.in website at home. So here my email, last line is my email ID, bpajith@gmail.com.
Okay.
So if you remember the xspice.in or the name xspice.in, the website. So once you come there, you have my email ID also there, bpajith@gmail.com. And then here about the hardware availability, that was another question. So here we have some numbers, or you can directly contact Jiten, this is Spark Research, this number here. For hardware availability, details are there, email ID and other things. And my email ID, bpajith@gmail.com.
So participants can take the email ID from chat box. Sir has already, Jitin has already shared it. And people who are asking for teacher training program, I think there is Irfan Mohammed also asking for that in Pune region.
Location, I mean,
So,
see, if I see,
yeah, they can directly contact by email, I think, Professor Ajith.
yeah, because we
With
can
their
plan something
queries.
up to, it's
And ma'am, Rekha, Professor
Yeah.
Ahluwalia has also joined, so I would like to
Yes.
invite him to give the
Yes,
concluding
yes.
remarks.
Yeah.
So thank you very much, Professor Ajith, for such a wonderful. We were very keen to have you here in this program. I think this is one of the best innovations which has happened in the last 20 years in the country. And gradually it has really developed into what we saw today. I think I have a few things which I wanted to share with you on behalf of IAPT, because if IAPT has to really take advantage of what you are doing, I would suggest, why don't you float an IAPT network of XPIs in the country? Because we have 24 regional councils plus some sub-regional councils also. So I was seeing that lately you have been concentrating in Kerala.
Yeah, right. That is because the Academy of Physics teachers here, APT. So they
So
see,
now I am saying that you connect with the IAPT and you can reach out to the people by visiting different RCs to generate these programs. That is why my suggestion, let us think about it.
Yeah, I'm always open to that. The only thing is, if somebody just chart out a plan, like, connecting one place to other. So in one round, because these workshops also I did like that, say something like 5 of them in a series. I go from, say, Cochin Kottayam like that up to, Trivandrum, 2 days coverings, like, so that way, like different RCs, we can have a kind of, 2-day one and traveling
in
to
fact,
another place.
Suppose I'm sitting in Himachal Pradesh, you come to say Shimla. So you don't just confine yourself to Shimla, but move around Himachal Pradesh, courtesy the Regional Council of Himachal Pradesh itself of the IAPT, and conduct this kind of a program. And I think that will be great. Another thing which is there is, I know that conducting all these things are online. When we are talking about it, is something which immediately says that, okay, these are to be done. But we can also convert it into a kind of a MOOC, in the sense that we conduct it for a month, not just for, say, a week or so. And we say, okay, one of the conditions to join this program is that you will get at the subsidized cost this hardware also. So once you say that, maybe lots of people can be trained in a faster manner. So you can try to, look at this part also, that how they have got those C-Lab on their table, and then they do it step by step as instructed in the classroom itself. If you can really think of doing that project also, I think that will be a great thing.
Actually, what had happened is, since you have mentioned that, I forgot to tell that. See, I run a learning management system, this Moodle site.
Yeah.
And I created a course on this, actually. I'll just show you that, since you mentioned that. I forgot to mention that, actually. And but we didn't take it up really, seriously. That's what happened. It is in the say school.in website. Well, let me just alpha.
Yeah, Alpha Moodle is there, yes.
Alpha.school.in. So here, let me just log in as a guest and go to, say, XPIs with Science. So I created a course, but it's basically never used. That's what happened. So it's
actually,
always
now
material.
I'll suggest you, I think once it is there, let us float this program as part of IAPT activities.
Because here, if you see this LCR, which I was talking about, including all the theory, everything is put there. But basically, I never.
So, Professor Ajith, what we are doing lately is this, that we are encouraging these kinds of things by conducting programs over a period of 1 month. So if this Moodle course is there, Let us really start thinking about it. One of the RCs can take up it and take responsibility for conducting it also. So if it is already there, I think half of the job is done.
So, but another thing is somebody from the academy, with the teaching side, should come and suggest the changes, because since I've been not in the teaching field, so whatever I put may not be the optimum. So if some suggestions come, if somebody goes through that, and I can change it to suit the need of because what students require, better. I mean,
actually, let's do this like this. Let's gather 40 teachers, let them come into that classroom, and let them really start doing these things and making you suggestions also. I think that will be a very interesting way of proceeding forward. Another thing
we need one offline meeting probably. Maybe I make a visit there and to get somebody either Delhi or Himachal, wherever people can come. Maybe we have a sort of meeting to get started. Then later on go online, or
maybe later we can sit down, Professor Ajith, in a meet and then talk about the details in it. I think I would love to really get IAPT going ahead with it in a big way, because IAPT has those means in terms of the network. Look at the NANI network, which is there of IAPT, National Anveshika Network of India. We had a coordinators meet in Himachal Pradesh, in which 30 to 40 coordinators from different parts of the country joined. I think the same synergy needs to be created in the case of your effort. And I think national education policy has all those elements in it, which can really spike the usage of this wonderful resource which you have created. So that is one thing which I would definitely love to talk about. Another thing which is there is, I'm seeking your help also now, because as an IAPT president, I think I should keep on asking experts if they can help us. You have this Moodle platform. I was immediately seeing that you have a question bank also. IAPT also wants to create a question bank in terms of Moodle. And can you really help us? Maybe we can sit down separately, that how this kind of
this question bank is not Moodle based. That is basically a online Postgres database where the questions are put there and a small code is there to generate question papers.
If it is that simple, it will be very fine for us also, if it is not that costly.
Oh yeah, actually it's a fairly simple affair, and its code is there and open, and one can try. Otherwise, if you need any help from me, I'm always there.
I think we will catch you. We will catch you on that count also. Exactly. Another thing which was coming to my mind when I was listening to your lecture, I think I have not skipped much in it. I could see it. Unfortunately, in the first 5 minutes, I had some guests, so I could not join them. But that is, do you really feel like conducting a kind of a offline workshop in which people come and make their own kit C-Lab, provided they are given some components, etc.? What is the feasibility of that kind possible?
Oh, that basically, if you see at this one, we can try. There is another small board called Kutipai that based on that, because this is a 4-layer PCB. It's a fairly very complex board actually.
Okay.
And hand wiring the boards, normally chances of getting it working is also very thin. We had that problem earlier. So this is all machine assembled.
Okay.
So it's a bit, but we have, if you want to put that in the Arduino line or something, like that is where people wire some hardware. But what they can do is, like this device which I showed you, that time of flight thing.
Yeah.
There are many other accessories, experiment setup which they have to make. Like for example, the air track, our linear air track. If they can make an air track, this Jitina showed you the distance sensor. So on the air track, we connect the distance sensor and move something back and forth. We can get the position data, so we can differentiate it to get velocity. So there is dozens of accessories have to be made actually. And I'm not even this one. My friend who was working in the UAC, so he is there in Southern Kerala. He got it made for me with some guys. Can you see this, right?
Yes,
So
yes, I can see.
similarly, basically, see the XSpice device at the core, it has some functionality, but when you keep on adding these things, there are many things which we can do, like something in the experiments which I didn't show us, like a filter. We just we teach filter circuits and all, and we could easily
I have those slides ready for filters.
do that with this actually. Just
I think the best part of all of your efforts is this, that there are lots of add-on features which are possible in it once you start thinking about those. So
yeah, we can expand it, expand it anything like that.
That's just great. So I think when we were planning this lecture, Professor Ajith, I particularly requested Ma'am Sapna to ask you that if we can add the word indigenous to this, because it's a great
indigenous,
effort,
right? Yeah.
and we made sure that it is projected like that also.
No, it is. When you see the idea, see, thing is, when 2000, that time, we see, there are many people, like, first thing who were, like, when we started this project, that time Professor Mehta was our director. So he and Dr. Arun Niguekar, UGC, and so a lot of people, they wanted to, create something. And fortunately, we had some kind of, expertise because of the accelerator related work. So, but it definitely started as an indigenous effort because we knew that the important substitutions, like Professor Verma ji at Kanpur had imported certain things. One lab was set up there with all these sophisticated. But he himself told that it's not affordable only. An IIT can probably do that. But and he was also very, and Nishika also, they have, he buy these kits and, conducting programs. So that was basically, it's an indigenous effort because that important solution we cannot really afford at all. That is, and it is kept as open source. That also, it's the main point is, since it is open source, suppose if it scales up into very high magnitudes, so say now Jitin is supporting, he is doing some manufacturing and, he's making it available. But suppose say tomorrow, if he is not there, we can always, find somebody or we can get it to, because the design is open and the software, of course, it's all, in the open. So we are on the safe ground there that way. Rather than imported equipment. Imported equipment, an oscilloscope goes bad, it goes bad.
Yeah. In fact, there was another thing. I was having a chat with Professor Ray Bakker, and he was talking about all these experiments which he did in Pune University.
Yeah, so he was very instrumental in putting in the syllabus and all in the beginning. Yes. And I'm in touch with him. Unfortunately, I could not go and meeting. His son's marriage was recent. So I booked the ticket and last moment something came up. I could not
So on behalf of IAPT and on my personal behalf, I would like to thank you. And I think those small triggers which I have shared with you, let us try to work on that and see what we can do. And
so you, forward. You contact me anything, from my side, if it is coming there, conducting or, whatever activities, it's possible. Because now, you know that after retiring now, it's more free time is available. So it can be utilized.
Thank you. So Sapna?
Thanks.
Yeah. So thank you very much, sir. It was a wonderful talk. So I would like to thank you. I would like to thank Professor H.K. Sajwani ji for chairing this session. Thank you very much, Ahluwalia sir and Ma'am Rekha. I think we are quite late also, but the talk was so interesting. It was so interesting. Thank you, Yogesh sir, for joining us. And thank you all. So have a nice good night. No, it's not. Good night.
Thank you.
We will have a session at Dharamshala.
Yeah. Next session will be at Dharamshala also. And
Professor Ajith, you are invited to attend that convention at Dharamshala.
Sure, it's in October. It's in October.
It's in October.
October at what? Shastri will be there.
October at what date? October, there is
16 to 18.
16 to 18.
That he knows because October I cannot.
Yeah, and one day workshop, pre-conference workshop is there.
That he told me,
that, but probably Satya will take care.
Yeah.
That he has.
Yeah, one of you
So
can definitely
Yeah.
conduct a workshop.
Thank you.
There
Thank
was
you
a
very
probability, but now it seems to be slightly different. Yeah.
Okay.
Mm.
Thank you
Okay,
so
thank
much,
you
sir.
all.
Thank
Thank
you.
you all for
Thank
joining
you.
today's session.
Yeah.
Thank you all. Good night.
Thank
Thank you.
Good night.
Thank
Good
you.
night.
Good night.